Hello everyone. I'm going to talk about chemical equilibrium. This is a new concept in this chemistry class. You will learn about chemical equilibrium by more details in general chemistry courses. But in this class, in this level, we are going to define chemical equilibrium by basic and simple definition. Whenever we are going to study chemical equilibrium, we need to have a knowledge of rate of chemical reactions. Let's see what is the meaning of rate of chemical reactions. As you see here, based on the definition reported on the slide, this is a measure of how fast the reaction proceeds. We are going to know what does that mean. It means if we have a chemical reactions, reactants, they are going to combine, they are going to mix together, they are going to make a chemical bond, they are going to break chemical bonds, and at the end, they are going to produce products. If all of these happen in the short period of the time, we say that our chemical reaction is fast. If it takes time to be completed, we say this is the slow chemical reactions. These two terms, fast and slow, they are going to represent rate of a chemical reactions. Rate means speed or velocity. They are terminology we use in different sciences, physics, chemistry. Whenever we are going to study the chemical reactions, we prefer to use this term rate, and we are going to represent our reactions is going to be fast or slow. Fast means reactants reacts in a short period of the time to produce the products, and otherwise, if it takes time, it means we are going to have longer time and we have a slow rate. Please remember that I'm going to talk about chemical equilibrium, each term, equilibrium, and I started talk about the rate of reactions. Right now, I'm going to connect the rate of reactions to equilibrium. If we are going to study chemical equilibrium and we don't have any idea about the rate of the reactions, we cannot study our concept. So rate is going to measure how fast a reaction proceeds. Please keep in your mind whenever I'm going to apply this information for our chemical equilibrium. And I'm going to relate the meaning to relate the rate of reactions to equilibrium. Before working on the chemical equilibrium, we are going to know why do we have for some reactions they are going to happen very fast in short period of the time, and some reactions they are going to be longer. It takes time. In chemistry, we have one theory, we call that collision theory. In collision theory, we say that reactants should collide each other. After collisions, they are going to make a new bond and they are going to make products. If we don't have enough collisions, it means we do have a longer time to see our products in the reactions. Collisions, it is going to help us to have a faster rate for the chemical reactions. How to increase the collision? One of those is using the heat. One of those is when you stir by tablespoon, if you stir by stir rod, if you shake your container. So you are going to help, we have more collisions between the reactants. If you are going to shake something to mix, so you are going to help, we have more collision between different molecules. So they are something we are going to work in our chemistry class. In collision theories, that I'm not going to work on this by details because this is not in our concept that we are going to work on. We have two different energy collisions. High energy collisions, low energy collisions. High energy collisions, it means we help the molecules to collide each other by more energy, too fast. Low energy, it means it takes time to collide between them. So we are always going to make high energy collisions to make products. And low energy collisions, it takes time, or sometimes we don't have any reaction between reactants. Sometimes we use another terminology, we call that activation energy. Activation energy, it means energy we use to activate our reactant to collide each other. This energy is going to help us to make more collisions. So if you heard something regarding the activation energy, you may imply that the energy just used to make more collision between the reactants. At that time, we are going to have our products. So whenever we are going to talk about the activation energy, I told you one of those is shaking your container or using the tablespoon to stir the reactants. But in chemistry, we are going to work with these two factors. One factor is concentration of reactants, and another one is the temperature. In general, before moving forward and talking about the other slides, when you see what happens in the chemical reactions, for temperature, it's obvious. If we have higher temperature, molecules have more energy because they have higher temperature, they move faster. When they move faster, they collide. So we have more collisions. More collisions means we are going to have their products in short period of the time, or we have fast rate of reaction. Another one is concentration of the reactants. If we have too much of each one, too much of two reactants, so it means they are going to collide each other because we have many molecules from each reactants. So we have more chance to see the collisions between them. More collisions, again, means we are going to have products in the shorter period of the time. I'm going to explain for you how concentration affects on the rate of the reactions. Assume that we have these two reactants, hydrogen and iodine. They are going to make HI. So as you see here, if we have low initial concentration, we have only, for example, 4 of each one, 4 hydrogen molecules, 4 iodine gas. So the collisions between them, it may happen. But look here, we have enough space and they need to move and collide each other. Let me work with the last one, high initial concentration. As you see here, we increase this number to 8, 2, 4, 6, 8. 8 molecules of hydrogens and 8 molecules of iodine. So it looks we have more chance for collisions. So whenever we have more collisions, it means we are going to have the fast rate for our reactions. So if you increase concentration, it means you are going to get the result very fast. That is why when you work in the chemistry labs, we prefer to work with the concentrated compounds because we are going to get the result in short period of the time or very fast. How temperature affects on the rate of the reaction? Again, assume that we have like this H2 and iodine is going to make HI. If we have low temperature, molecules move, but they don't move fast because they don't have enough energy, and whenever we have collisions, we are going to make the products. But if we use high temperature is going to make molecules move faster. When they move faster in this container, they have more collisions. More collisions, it means we are going to make more products in the short period of the time. So high temperature is going to make the fast rate as well. So if I'm going to summarize all information I reviewed here, if we increase concentration of the reactants, we are going to see faster rate. If we increase the temperature, we are going to see faster rate. Again, I'm going to talk about equilibrium. You understand the meaning of the rate of the reactions. Right now, please look at this slide. I'm going to apply another concept, and after that, we are going to combine these two. When we say a reaction, we are always talking about forward reaction. But if products is going to combine and make reactants, so these two react to each other to make products, and these two can combine by each other and make reactants. The left to right reaction, we call that forward reaction, and if we have right to left, so we call that reverse reaction. So this terminology I used here, reverse reaction, forward, reverse reaction. Forward means reactants, they are going to make products, and reverse, it means products, they are going to make reactants. At that time, we call that reaction is reversible reaction. So we have two directions for our reaction, forward and reverse. Chemical equilibrium, it says if rate of forward reaction is same as rate of reverse reaction, it means we have chemical equilibrium. So for specific reactions that we have forward and reverse reactions, we are going to say if rate of forward reaction is same as rate of reverse reaction, we are going to make equilibrium or chemical equilibrium. Look at this reaction. This is example of reversible reaction. NO2, nitrogen dioxide, is going to produce N2O4, dinitrogen tetroxide. This reaction, we call that forward reaction. If products, they are going to make reactants, reverse reaction. N2O4 is going to make NO2. We call that reverse reaction. I use heat to make sure we are going to work on this by another factor as well. If rate of reverse reaction and rate of forward reaction is going to be same, is going to be equal, we are going to say we have chemical reactions. We are going to say we have chemical reactions. One of the factors you are going to study equilibrium or chemical equilibrium is one constant, we call that chemical equilibrium. One constant, we call it chemical equilibrium. Let's see what does that mean. Assume that we have this reaction, forward, reverse reaction. Whenever we are going to write chemical equilibrium, we write products on the top and reactants on the bottom. So this is a convention. Products on the top, reactants on the bottom. We need to know concentration of each substances. So I use a bracket to represent concentration. Concentration of C, concentration of D, concentration of A and B. If we have coefficients, coefficients appear as exponents. If we have coefficient C for this substance, so we write that one as exponent for this. Please look at this example. Reverse reaction, forward reaction. Is very obvious which one is forward, which one is reverse. Always we write products on the top and reactant on the bottom. Products on the top, NO2, O2, N2O5. Then we are going to apply coefficient as exponent. Coefficient for this substance is 4. I write exponent. This number is 1 because coefficient for oxygen is 1. So we don't write 1 here, like we don't write it as a coefficient. So this is the general formula for this specific reaction. We call that chemical equilibrium. We have forward and reverse reaction. One thing I may ask you to pay attention whenever you are going to work with the chemical equilibrium, please exclude liquid and solid. Please exclude liquid and solids when you are going to write the chemical equilibrium. So in this example, we do have gases. So we write all of them in the reaction. If in case we had liquid or we had solid, don't write this one. Whenever you write this, cross that one. Because liquid and solids, they have constant concentration and rarely they change in the chemical equilibrium, and we don't consider them. I'm going to explain for you by the next slide. Look here, equilibrium constant, if we calculate this at 25 degrees Celsius, you may find this number is too large, or you are going to calculate for this is going to be too small. So we are going to interpret what is the meaning of large or small chemical equilibrium. If we have this reaction, hydrogen, bromine, they are going to make HBr. So if we calculate that, we will see we have a large number. How to find a large number? So please look at this notation. Hydrogen is the only gray or white one. And this brown color represents bromine. So you see the bromine. And we are going to make HBr white and brown. As you see here, we have many white and brown, many products if we compare by the reactants. So we say that chemical equilibrium is going to be large if we have too much products comparing by reactants, too much products. So as you see here, we have low concentration of the reactants and we have too many molecules appear here. So our products are concentrated and we have low concentration for reactants. If we have like this one, let's look here. Nitrogen, oxygen, nitrogen monoxide. Blue means nitrogen, red means oxygen, blue-red means nitrogen monoxide. As you see here, if you compare the molecules, we have few number of products. It means we have low concentration of products. We don't have many of them, only 1, 2, comparing with the reactants. So at this time, we have low concentration of products. So we say we may have small numbers. So please look at these two equations I explained for you. Big number, large number, it means we have more products. And a small number, it means we have low concentration of products. Mostly we have like this one. If I'm going to explain that one, I'm going to explain by this slide. If equilibrium constant is smaller than 1, it means we have more reactants. It means reverse reaction is favored by the system. I'm going to talk about this terminology a little bit later, but reactant side is favored, more reactants. If we have chemical equilibrium is too large, it means we have more products. It means product side is favored. System prefers to go to the forward reaction and progress in the forward reaction. If equilibrium constant is 1, it means neither reverse or nor forward reaction is favored. Look at this. This number is too large, so it means we have more products. It means this reaction mostly happened by forward reaction. We are going to produce this, HBr. This number is too small, means more reactant. Between these two reactions, system prefers reverse reaction. It's going to back and produce these reactants. So that is why we say reverse reaction is favored. So if you remember, I told you whenever you are going to write chemical equilibrium, please exclude solid and liquid in the formula. Look at this reaction. Calcium carbonate, solid, is going to produce calcium oxide, solid, and carbon dioxide gas. If I ask you to write chemical equilibrium of this reaction, you might write the products on the top divided by reactants on the bottom. You have solid, so you just need to remove solid here. So the only thing remains is CO2. So if you write the chemical equilibrium, you will see CO2, CaO, CaCO3. But you need to cross CaO and CaCO3 because they are solid. So we remove solid and liquid from our equilibrium expression. How to calculate equilibrium constant? So always you are given the concentration. For example, in this equation, I may ask you, based on this given info, calculate equilibrium constant. So first you need to write chemical equilibrium formula, Hi gas, iodine gas, H2 gas. So we write all of them. The coefficient should be as exponent. We write it. So Hi in the bracket square divided by H2 divided by I2. Then I'm going to plug in the equation. H2 concentration 0.11, I write it. Iodine 0.11, I write it. Hi 0.78, I write it. So you just need to calculate that one. And then you should report your answer by proper suffix. So chemical equilibrium is going to have different units. It depends on the reaction. So there is no unit for this one because we have we have molar square here divided by molar times molar. Molar square divided by molar square is going to be cancelled. So there is no unit for this example. But for other examples, we may use the units. It depends. Please look at this example. I say, for example, chemical equilibrium at 1000 degrees Celsius is 2. As you may remember, temperature is going to change the rate of reactions. So we need to know we are going to study at what temperature. So temperature is additional information. You don't need to be worried about that one. So you have chemical equilibrium for this reaction. If this information given and you are asked what is the concentration of carbon dioxide, let's see how it works. This information given, I'm going to calculate carbon dioxide concentration. All right, chemical equilibrium. CO2, CF4, they are products divided by reactants. We have coefficient We write the coefficient for them. All of them are gases, so we keep all of them. Then I'm going to rearrange this equation, or you may plug in here directly. So concentration of this, I'll write that here. Concentration of CF4, I'll write that here. Equilibrium is 2. Then you are going to solve your problem. If you solve your problem, at the end you may get this number by proper sequence. This is the problem I may ask you to do by yourself and see are you able to get the number like this example or not. Let's look at this example. We have this general information. A is going to produce B, B is going to produce A. Forward reaction, reverse reaction. We reviewed this reaction in three different temperatures. We are going to know at which temperature is the equilibrium constant is largest. We have highest equilibrium or largest equilibrium constant. For our notation, we use the red color for A and B color and blue color for B. A as a reactant, B as a product. Please compare these three temperatures and see which one is going to have largest equilibrium constant. To remind you, largest equilibrium constant, it means we are going to have more product, forward reaction. More product, it means you just need to count which one has more blue color. See which one has blue color. As you see here, in this part, we have more blue color. So at T3, we have largest equilibrium constant because we have more products or we have less reactants. So this is like this. And finally, in this chapter, we are going to work on one principle in the chemical equilibrium by this principle just studied by one French scientist, and we are going to work with that one, the Chatelier principle. So we are going to work with this one. It says when a chemical system is at equilibrium, it means we have equilibrium system, and we disturb that one. We disturb the equilibrium. We change the stability of the equilibrium. The system shifts in a direction to minimize the disturbance. The system is going to relieve this disturbance. We are going to see what does that mean. Please look at this slide. N2O4, 2NO2, reactants, product, forward reaction, reverse reaction. We add manually, intentionally, we are going to add NO2. We increase concentration of NO2. The system is going to remove this additional NO2. To do that, it's going to use NO2. The only reason is going to remove or use NO2 because it's going to back to the equilibrium. The only way is going to remove or use NO2 is moving to the left side, shifting to the left side. Shifting to the left side, we say reverse reaction is favored. So if I add, for example, in any reactions, I add one of the concentration, system is going to use that one and shift to the another direction to consume that specific reagent. So we call that shift to the left or reverse reaction is favored. So this is the example you are going to see by your diagram. N2O4, NO2. So as you see here, we have NO2. We are going to add NO2. We add NO2. So Whenever we are going to add NO2, they are going to combine and they are going to make N2O4. They are going to make N2O4. That is why we see more N2O4 in the system. As you see here, if I add N2O4, if I add N2O4, so the system is going to produce NO2, shift to the right, So if we add N2O4, it's going to shift to the right to consume N2O4 and produce NO2. Look at this reaction. This is the H2 reacts with nitrogen to produce ammonia. If we add H2O, let's see what happens. If I add H2O, system is going to use additional H2O. So it's going to consume that. So it's going to shift to the right. Shift to the right, it means we are going to have forward reaction is favored. If is shift to the right, it's going to produce NH3. So we are going to produce more NH3. Shift to the right, it means we are going to consume hydrogen and nitrogen. The nitrogen and hydrogen concentration is decreased when we are going to produce NH3. So if you add additional hydrogen, it's going to shift to the right and produce NH3. If we are going to summarize based on the systems we reviewed in our class, we are going to say like this. If I add reactant, system shift to the right and produce product, and is going to reduce reactant. If I add reactant, shift to the right, producing product and reducing the reactant. If I remove reactant, so we don't have reactants, we don't have enough reactant, the system is going to produce reactant. Shift to the left to produce the reactants. So reactant is going to increase and product is going to use, so decrease. Same scenario if we are going to apply this information for products. Adding product, removing product. If I add product, more product, so we are going to remove that one. We are going to use this one. So shift to the left. We remove product, increase reactant, and decreasing product. And finally, if we additionally decrease the product concentration, so we are going to produce product by the system. So system shift to the right and is going to produce product and is going to use all reactants. So you will find this information for any examples we work on this. Look at this one. We have this reaction, reverse and forward reaction. In the lab, we are going to see how it works. What color will be observed if ammonia is added to the equilibrium mixture? Ammonia is here in the reactant. We add reactant. Please look here. We add reactant. System shift to the right because it's going to back to the equilibrium. It's going to produce product. So NH3 is going to added by chemist. Additionally, NH2 system is going to use that one. System shifts to the right. So we are going to see royal blue color. So if you add NH3 here, we see more royal blue color. So when you work in the lab, this color change, it represents the system prefers royal blue. System shifts to the right or forward reaction is favored. So please look here. If I add NH3, the system is going to use NH3 and Cu2 plus. So Cu2 positive and H3 are going to use up. So their concentration is going to decrease and we are going to make more products. It's going to increase. How about this one? Adding CH3COO negative. Whenever we are going to work that, adding acetate, as you see here, is going to make more products. So system is going to shift to the left. Shift to the left means making more acids. Use these two reactants because we increased this one. We are going to study that one. If we increase acetate, this one, system shift to the left because it's going to use these two reactants. So the concentration of these two is decreasing. We are going to make more acid. So whenever you make more acid, so it's going to make more reactants. As you see here, you will see like this one. You will see like this one. The pH is going to be changed based on the additional acetate. Acetate can be found in the two different forms in the chemistry as you see here. How about if we add NaOH? If we add NaOH, look here in this reaction, there is no NaOH. When you work in the lab, if you don't have a compound in the reaction, it means we have another reaction. We have a reaction between this substance and one of these substances, compounds, ions in the equilibrium system. NaOH is not here. But NaOH is a base. If I add NaOH, NaOH is going to react with acid. NaOH is react with acid. So whenever NaOH is react with acid, it means we are going to decrease the concentration of these two. It means we are going to decrease concentration of acid because acid is not participate only in this reaction. It's going to react with NaOH with another reaction. So we don't have enough acids. When we don't have enough acids, system prefers to produce acids. So system shift to the left. System shift to the left. And whenever system shift to the left, we are going to make like this one. Let me ask you, what is your prediction if we add concentration of nitrogen? Nitrogen increases, system shift to the right to remove additional nitrogen from the system. So shift to the right. If we say shift to the right, we should say that forward reaction is favored. So both are same. Both are same. So you see the changes here. How about this one? If we add chloride ion, I add chloride ion, so system has additional chloride ion, shift to the left to produce AgCl, so favored reaction is reverse reaction, shift to the left. So system is going to use up Ag plus, Cl minus, and produce AgCl. What color you will see if you react your system, your reaction by additional HCl. We add HCl to the system. HCl is not in the reaction. is going to be one of the new reaction with one of these. NH3 is a base. So if you add HCl, it's going to react with base. So it means you are going to remove NHCl from the reaction. So always, whenever we add a new substance, you cannot see in the reaction, it means we are going to remove one of the substances. This substances is NH3. So I'm going to remove NH3. So whenever NH3 removed from the system is going to produce that. How to produce this? Shift to the left, and we may have pale blue. How about this one? How about this one? If iodine added to the system, what happened for concentration of hydrogen? Iodine is additional, so your system is going to reduce that. System is going to remove that. Shift to the right, and we are going to produce HI. When we are going to produce HI, we are going to consume iodine and H2. Question says concentration on H2. We need to use it, so decreases. Concentration of H2 decreases. So there are something I wanted to show you by the different slides, different examples, and diagram as well. So we already review everything. Last factor I'm going to talk about this before talking about the one specific part is the volume. Guys, volume is going to affect only when we have gases, gas mixture. So if you have liquid or solid, if you have aqueous, you don't need to consider them in volume change of the equilibrium. Please remember, based on the gases law, volume and pressure, they are inversely proportional to each other. If volume increases, pressure decreases, and vice versa. Please remember Boyle's law. So if we say increasing volume or we say decreasing volume, means we are talking about pressure as well. So you just need to know, if we say decreasing volume, it means increased pressure, or vice versa. Increased volume, it means decreased pressure. What happens if, please look at this example. We have 4 moles gas, 2 moles gas. Whenever we are going to study volume change in the equilibrium system, you just need to count the gas molecules. On the reactant side, we have 4 mole gas. On the product side, we have 2 mole gas. Look at the coefficients, 1 mole gas, 3 moles gas, totally 4. Here we have only 2. If you decrease the volume is decreased, the system shifts toward the fewer moles of gas. Volume decreases, so system shifts to fewer moles of gas. In this example, shift to the right. Why do we have like this? The volume decreases. There is no space here. System doesn't have enough space, so it prefers to produce fewer moles of gas. So left 4 moles, right 2 moles. So there is no space for the system, so it shifts to the right. If we increase the volume, at the same example, if we increase the volume, so system has enough space, system has enough room for the molecules, so it has enough room, so it prefers to make more moles gases. So shift to the more moles gases. We don't have any rule like the concentration, so you just need to count the moles of gases and work on this. So to summarize the information I give it you, Decreasing the volume, it makes the system shift to fewer moles of gas. Increasing volume, more mole gas is favored by the system. If we have same number of moles for gases, no change, no effect for the system. And if you remember, I told you equilibrium is going to be same like 1, neither forward nor reverse reaction is favored. Please look at this example. Sorry. Please look at this example. We say we are going to decrease the volume, decreasing the volume. So all of them are gases. Decreasing volume, it means we don't have enough space. So here 4 moles, on the right side 2 moles. So shift to the right, shift to the right. So, and scenario is going to be repeated like the concentration. We are going to make more moles gas for NH2. So in which direction will the equilibrium shift when the volume of reaction vessel is decreased? Reaction container, we are going to make a smaller one. So system is smart, system is intelligent, system prefers to make fewer moles of gases. It's going to make PCl5, shift to the left. How about this one? We are going to increase the volume. We are going to make a bigger container. So more gases on the right side. So shift to the right. For this example, if volume decreases, so no moles gas on the left, no moles gas on the right, no gas means nothing, no change for that one. Volume is going to change only when we have the gases. So you should select this option, no change for this reaction. And finally, I'm going to remind you only 2 types of reactions we have, exothermic, endothermic. In exothermic, it means we are going to produce heat, and endothermic, we are going to gain heat. For exothermic reaction, we can think heat is a product because we are going to produce heat. So what happens if we have higher temperature? Product increases, system shift to the left. How about endothermic? Endothermic, it means we gain heat. So heat is a reactant. How about if we increase the temperature? Heat is a reactant. Increase temperature means increase heat, increase reactant. Increase reactant, system is going to use that one. Shift to the right. So let's see what happens. Look at this reaction. This reaction is exothermic, because heat is going to produce. NO2 make N2O4 and heat. Heat is produced. If temperature increases, we have too much heat. System is going to back to the equilibrium. Is going to use the heat. System shift to the left. So we have more brown gases. So as you see here, at 90 degrees Celsius, high temperature, we have more brown gases. If we have low temperature, so system is going to produce heat. It's going to produce heat, more products, so more colorless gas. As you see here, in lower temperature, we have more colorless, or this observation happen for this system. Answer the question, how will an increase in temperature affect the equilibrium concentration of ammonia. Increased temperature means increased heat. System is going to shift to the left, using NH3 to produce nitrogen and hydrogen. Using NH3 means decreasing NH3. Please read that one to make sure you understand this. For this reaction, how about this one? System is going to be cooled, lower temperature. I'm going to have lower temperature. Heat is going to be lower temperature. So we decrease heat. System is going to produce that. System is going to produce heat, produce PCl5. System shift to the left. Hope you learn these examples for equilibrium system. Thank you for watching.